So let's try to start the introduction of principal component analysis. So principal component analysis, essentially, we're trying to find a linear projection operator to project the originally observed input feature vectors into the subspace. So because it's a linear projection, and the functional form of this linear projection is essentially the linear combinations of original observed features. And then again, like all the other machine learning algorithms, we need to somehow have the performance evaluation metric to measure whether those linear combinations are good or not. So one way to explain principal component analysis is that after the linear projection to the subspace, we want to maintain the distribution of the data points in the original space. So one way to measure the distribution or spread of the observed measurements in the original space is variance. So basically, we're trying to maximize the variance after the projections. And then all those corresponding dimension of the subspace after the projection is known as the principal components. Here basically are the potential mathematical notations for principal component analysis. Again, principal component analysis is a linear dimension reduction method. So this X here is original input feature vector, which is in D-dimensional space. And we are going to find a subspace with dimension R is definitely going to be less than D. And we are trying to find this linear transformation function F from the original input feature space to the reduced subspace. And then because it's a linear projection operator, so we indeed can use a transformation matrix or projection matrix V, which is a D times R dimensional matrix to derive the linear projection. So if you know about this transformation matrix or function, then given a feature vector, then you can do the projection to find the reduced representation Y. And actually, typically, this Y is also known as a principal component scores. So in the corresponding principal component direction, you are trying to find the projection. This projection is the principal component score. So now you have a training set of the input feature vectors, and then you're trying to maintain the variability or spread of this training set as much as you can so that you can derive this corresponding V matrix or the transformation matrix. If you, again, similar as a linear regression, write all the training samples in a matrix form, then you basically can write this capital X as a matrix. So each row is a corresponding observation with D dimension feature vector or D measurements. So each column is a corresponding measurement or corresponding feature. And then if we write out that, then the principal component scores for all those n observations or m data points is essentially just the X transformation matrix of V. So if you try to look at the dimension of the matrix, the X dimension is n times D, V dimension is D times R, X times V will be a matrix with the dimension n times R. So you get the R principal component scores for each corresponding observation. So in fact, based on that, then you can try to formulate the optimization formulation, trying to make sure the variance of the corresponding this principal component scores is largest. And then you can solve the optimization formulation and find how you can derive this transformation matrix of B. But let's make things a little bit simpler. So instead of looking at R principal components, we are only going to look at the largest principal component. So we are only setting R equal to 1. So V now is just a vector. V is D times R. So R is equal to 1. V is a column vector with corresponding D dimension, which is the input feature vector dimension. And then we rewrite these relationships for linear projection by this matrix vector multiplication. So because we only want to find one principal component, then each observation will have only one principal component score. If you remember what we did with the linear regression model, then this essentially is very similar as a linear regression functional form. But because now we don't observe y, we are looking at unsupervised learning here. So we need to have a different performance evaluation metric. So if you remember linear regression, we're using the residual square of sum, RSS, as a performance evaluation. We formulate the objective function. We minimize this loss function to compute beta or W in the linear regression model. But here we don't observe y. We don't know what y we are trying to get for the principal component score. So we have to come up with a different performance evaluation metric. So if you remember what I said is that I want to preserve the spread of the data distributions in the original input space by maximize the variance. So let me try to explain why this is a variance. So y1 transpose y1, if you write it out, it's I equal to 1 to n, and then y1 I square. So this is just the inner product, and then you just multiply the corresponding entries of this n times one dimensional vector, take the square and sum them together, you get this. If you know about how do you actually estimate the variance of the corresponding y random variable, you know that when we are trying to estimate the sample variance given the observed samples, then the estimation of the variance is typically equal to 1 over n minus 1 y squared I equal to 1 to n. So basically, y is the corresponding random variable, and yi is the corresponding sampled random variable realization. You sample it n times, and you are trying to estimate the variance of this random variable. The unbiased estimation of the variance is essentially equal to the 1 divided by n minus 1 and the summation of the square. Now, if you think all those principal component score is essentially the corresponding realization of your random variable of the principal component score, and this is proportional to the variance estimate. So if you want to maximize the variance to get the largest variance along this first principal component direction, then you are trying to maximize the inner product of the y1 vector. So that's essentially the connection of why when we are trying to derive the principal component analysis based on the variance, why we're actually trying to maximize y transpose y. So there are a couple of important things we needed to introduce to actually have a unique solution of the principal component direction or the projection operator V. One of the important constraint that you need to make sure we get the unique principal component directions is to make sure V transpose V is equal to 1, which is also known as the orthogonality constraint. So basically, when we are trying to identify the subspace, then we want to make sure the subspace, the direction has a unit norm. The reason is that you can easily multiplying V with a scale constant. So if the scale constant alpha, for example, increase to the infinity, then you will always increase the inner product of y. So that's why you want to make sure V transpose V is equal to 1, has a unit norm, so that you will derive the unique solution for V. So that's essentially the optimization formulation to derive the first principal component. And often, again, it depends on the implementation of the principal component analysis. Very often, you indeed try to first center or normalize the originally observed features by making sure all the features are centered around 0. If you follow this implementation, then we have this corresponding objective formulation to solve. So how do we actually solve this? You need to use the Lagrangian formulation again as we introduced in support vector machine. So basically what we are trying to do is to look at the Lagrangian formulation here with respect to V, which is equal to V transpose X V plus V transpose V a minus 1. We want to maximize this, so you need to change the sign to negative. So this is actually the objective function you are trying to optimize, and then you do the KKT condition. So basically one of the KKT condition is the first order derivative of this Lagrangian will be equal to 0. So you do the linear algebra or matrix vector calculus to compute the first order derivative of this Lagrangian with respect to V. What you can get is X transpose XV minus lambda V will equal to 0. So if that's the case, then you have X transpose XV will be equal to lambda V. So essentially, we are trying to find the largest variance. So this V is essentially the eigenvector corresponding to the largest eigenvalue of this matrix. So that's how you derive the first principle component using this optimization formulation, and then trying to solve the optimization, derive the closed form. And the closed form is essentially the eigendecomposition of this X transpose X design matrix. And if you remember, actually, we used this matrix for linear regression. So it's an inverse of this matrix times X transpose Y will give you the beta. So that's a very brief introduction. How do you actually solve for principal component analysis? And then, of course, you can indeed extend or generalize this optimization formulation, and so you can do it sequentially, or you can do it in a batch way. But at the end, you will end up with the same solution that you basically do the eigendecomposition of X transpose X matrix to identify the eigenvectors corresponding to the first R eigenvalues. Then this right eigenvector essentially give you the principal component subspace or directions for the projection. Now, if you are familiar with linear algebra or matrix vector manipulations, then indeed the principal component analysis can be also solved by singular value decomposition. If you have this, again, the original input feature matrix, you do the singular value decomposition to identify the left eigenvector matrix, right eigenvector matrix, as well as the corresponding sigma eigenvalues, which is a diagonal matrix. Then you can see that this V matrix essentially is the same transformation matrix as a solution to this optimization formulation. So why this is important? Because this is important in the sense that you can actually derive a computationally efficient way to derive the principal components, depending on whether you have many data points or you have really high dimensional feature vectors. So because of this flexibility of doing singular value decomposition, then you can always derive the computationally efficient solutions to derive principal components. And of course, after you derive the principal component directions or subspace, then you can always check the properties of the derived principal components. We already said about this. So the corresponding principal component is essentially the right singular vector of X or right eigenvector of X transpose X with respect to the ith largest singular value or eigenvalue. And then if you compute the corresponding variance or the inner product of the corresponding projected score or principal component score along the three directions, then you can check the percentage of the variance after the projections. This is essentially related to another optimization formulation of principal component analysis, like a minimum reconstruction error. So it is indeed equivalent to derive the optimization formulation based on the largest variance assumption or based on the minimum reconstruction assumption. So you can check on those two different objective formulations, and then you can actually derive the principal component. Directions are exactly the same thing. And the last part is actually when we are looking at different principal components derived based on these optimization formulations, the principal components are indeed orthogonal to each other because of the constraints we set up to make sure we get the unique solutions. All right, so this is basically a visual illustration of what do you get. So basically this is the original input training observations, and then what you are trying to do to find the first principal component, so you can project those original observations to this subspace. And you can see that along this subspace after projection, you have the largest spread or largest variance. If you are not satisfied with this first principal component subspace, then you can add the second principal component subspace. So in this specific example, if your original feature dimension is 2, then basically you capture all the variability in the original data points. But if you only use one dimension space, then you still capture a certain percentage of the variability of the original observations. So this is a very kind of deterministic way of introducing principal component analysis derivation. And there are also other way to derive a principal component analysis. Actually, one potential probabilistic model related to principal component analysis is known as a factor analysis. So factor analysis is actually a generative model. So essentially, we are assuming that all the input observations or measurements are coming based on these functional relationships of underlying signals. So this underlying signal H is a random vector, and we also call them as latent variables or latent vector. And we are basically doing a back projection of the signal so that we can get all those measurements, which again is a linear combination of whatever underlying signals you can have. And then you also have the assumption that the measurements may be biased by this U vector, and also you have a Gaussian noise epsilon when you're trying to get those measurements. So basically now with this functional relationships from signal to the observed measurements, then you can come up with a probabilistic formulation of observed measurements. And then what you can do is that you can use those W mu as model parameters, and you write out the likelihood function of observed data given this model. And then you solve the maximum likelihood estimation problem to find the W and the corresponding U and the long model parameters. And if you do that under certain settings, for example, you making the assumption mu is equal to 0, then epsilon has the same variance for whatever measurements you are trying to investigating, then you will end up with the same PCA solution strategies. So basically, you're again doing either the singular value decomposition of X or the eigen decomposition of X transpose X to derive this W matrix. If you don't care about the distribution of this W, then you will end up with the same eigen decomposition or singular value decomposition problems. All right, this is one example, which should be very simple example. You basically randomly generate the random samples in two-dimensional space, and then you call the scikit-learn principal component analysis, and you solve it for the first principal component, and then you identify this is indeed the direction that can achieve the maximum or largest variance. So that's one example. And then you can also implement the principal component analysis in this iris dataset. We have used the iris dataset in multiple supervised learning algorithms. It has 4 input features based on the flower shape parameters. And here we're trying to derive the 2 principal components into derive the subspace from original 4-dimensional input feature space. And then what we are trying to do is just to visualize all different iris flowers in this 2-dimensional space. You can see that with this principal component dimension reduction, you can easily visualize the differences across different iris subtypes. That's actually another important reason people are trying to do dimension reduction. So when you are trying to explore whatever available training sample to make sure what kind of patterns you may observe. It is easy to first reduce the dimension to either two-dimensional subspace or three-dimensional space, and then try to plot the distribution of data points in these reduced subspaces to see whether you have identified any organization patterns in the original training data points. And then you can decide whether you are going to, for example, use a linear or nonlinear or more complex supervised machine learning models to tell the differences of the data points. So actually this one, we indeed used it for support vector machine example. So we actually talked about this. Again, this problem is basically trying to recognize the faces based on the image pixel values. As we explained earlier in a support vector machine session, because the number of pixels are really large, it's more than 3,000. So instead of directly using that as input features, you first do the principal component analysis to reduce the number of features. Then after you reduce the original more than 3,000 pixel values into 150 principal component features, then you apply the supervised machine learning problems, for example, support vector machine to do the face recognition. And now if you actually indeed derive the principal components, then you can see actually those derived principal components, if you have enough number of face images, it does have certain meaning, whether it captures the lightness, brightness, or certain direction of lighting, or certain eye, mouth, nose relative locations in a given image, so you can make some sense of what you are observing. And another important thing, basically here we're checking how you are capturing the variability of the original training face image. So you can see that with 150 principal components, you indeed can capture more than 90% of variability of the training image.